Nothing. The total lack of everything. Humans hold the belief that something must have existed for anything else to come into being. So, how did it all begin? We claim it originated from nothing. But surely nothing cannot simply transform into something. Correct? In the immense cosmic vastness where galaxies gleam and black holes consume matter, a puzzling concept emerges. Nothing. This isn't merely a philosophical notion. It's a core element of how we comprehend the universe, and it's been fascinating scientists and thinkers throughout history. Picture a location in space where almost nothing exists. No stars, no planets, only void. It's somewhat like a silent region of the universe where the typical laws of physics don't function quite the same manner. Leave a like and subscribe to the channel as we embark on a journey into this enigmatic cosmic void where we'll discover the fascinating depths of space, explore cutting-edge technology, and uncover the layers of the puzzle that is nothing. The idea of nothing appears contradictory, and yet it represents a crucial concept in the domain of advanced cosmology and science. For those seeking to explore the universe's mysteries, comprehending what nothing genuinely signifies in space's vastness represents the initial step toward understanding the mysterious fabric of the cosmos. Initially, one could envision space's emptiness as a perfect vacuum absent of any matter or energy. Though this concept embodies a certain simplicity, it doesn't capture the elaborate reality we've discovered through scientific investigation. In contemporary cosmology, nothing in space differs greatly from an absolute emptiness. Rather, it constitutes a subtle and intricate terrain that questions our existing assumptions. Let's examine this concept through science's perspective. Against common intuition, space's vacuum isn't genuinely empty. It's brimming with quantum fluctuations, a phenomenon where particles and antiparticles spontaneously appear and eliminate each other. These fluctuations provide a dynamic and constantly shifting character to the presumed void. Space connects fundamentally to the structure of spacetime as Einstein's general relativity theory describes. Even in areas lacking visible matter, massive objects' presence can bend spacetime, influencing nearby objects' paths. When we look into space, we can identify the subtle echo of the Big Bang itself. The cosmic microwave background radiation represents a remnant of the early universe. A quiet whisper reminding us that space hasn't always appeared as we observe it now. Despite our progress in comprehension, the concept of nothing in space remains puzzling to scientists and philosophers equally. Speculation circulates regarding the potential for regions where matter density nears true nothingness, but these theories remain at cosmology's edges. One fascinating notion proposes that regions in the universe may exist where matter's density becomes incredibly sparse, approaching the void. These theoretical voids, should they exist, might provide essential insights into space's nature itself. Does empty space truly lack all matter and energy? This apparently simple question unleashes a wealth of scientific discoveries and philosophical contemplations. In the domain of traditional wisdom, space's void is frequently imagined as a perfect vacuum, an empty landscape without even the faintest trace of matter or energy. It's an attractive concept that aligns perfectly with our human comprehension of emptiness. However, as we probe deeper into cosmology's frontiers, we learn that reality proves far more elaborate and captivating than we could have conceived. In quantum mechanics' world, the subatomic domain that controls particles' behavior at the tiniest scales, we encounter a concept that questions the very nature of nothing. This concept goes by quantum fluctuations, and it reveals that even in space's most barren corners, particles and antiparticles can spontaneously appear, participate in a brief dance, and annihilate one another in a cosmic instant. These tiny and temporary events contradict our traditional understanding of emptiness and inject life into the void, generating a dynamic and continuously changing canvas. Furthermore, general relativity's theory, developed by Albert Einstein's brilliance, instructs us that space and time interweave intricately into a four-dimensional structure called spacetime. Massive objects present such as planets, stars, or even black holes can distort this structure, affecting nearby objects' trajectory. In this way, the concept of completely empty, unchanged space becomes an impossible ideal. How does nothing connect to dark matter's mysterious presence? And what does it reveal regarding the universe's complex tapestry? To address this cosmic riddle, we must initially wrestle with dark matter's essence itself. Unlike regular matter, which constitutes stars, planets, and galaxies, dark matter stays concealed from our perception, revealing its presence solely through gravitational forces it applies. Essentially, it represents the ultimate expression of nothing in the way that it escapes direct detection and resists conventional matter descriptions. Dark matter's presence became evident through galaxy observations and their movements. The gravitational attraction created by visible matter independently couldn't explain these galaxies' observed conduct. To close this gap, scientists suggested the presence of an invisible, intangible substance, dark matter, that occupies the cosmic voids and connects galaxies together. This mysterious nothingness of dark matter challenges our traditional comprehension of emptiness. It shrouds itself in invisibility and yet wields the cosmic power, molding the universe's very structure. It exemplifies how nothing can possess scientific importance and profound impact. Throughout the cosmic web, dark matter creates extensive filaments and halos, establishing the framework upon which galaxies and galaxy clusters form. Without dark matter's presence, the universe we recognize would appear dramatically different. The cosmos would miss the gravitational adhesive required to create the celestial bodies that have fascinated human imagination for ages. The Big Bang Theory suggests that the universe we recognize originated as a singularity, a location of infinite density and temperature roughly 13.8 billion years past. It marked a moment of cosmic beginning, an occurrence where space and time's fabric itself emerged from what could be regarded as nothing in traditional terms. But how does this theory, which depicts our universe's explosive birth, connect to the concept of nothing? To comprehend this, we must initially understand the singularity's nature. At the Big Bang's moment, the singularity signifies a condition where physics laws collapse. It constitutes a point of infinite density and zero volume, contradicting our typical understanding of matter and space. In this way, the singularity can be viewed as a manifestation of nothingness, a point where the universe lacked its recognizable structure and dimensions. However, this seeming nothingness contained immense potential. As the universe grew from this singularity, it experienced a swift phase of expansion during which space itself extended exponentially. In an instant, the universe changed from a state of cosmic nothingness to a churning cauldron of energy, particles, and the fundamental forces controlling our reality. Throughout the Big Bang's opening moments, the universe was extraordinarily hot and dense, appearing like a primordial mixture of particles and radiation. In a moment's fraction, it experienced a sequence of changes, including nucleosynthesis, where initial atomic nuclei developed. This cosmic development eventually resulted in stars, galaxies, and the elaborate structure we witness in the cosmos presently. In this framework, the concept of nothing assumes a dynamic and developing character. It isn't a static void, but a surface upon which the universe creates its own narrative. A narrative that commenced with the cosmos' explosive birth, Does space's vacuum hold any particles or fields? The question of whether space's vacuum genuinely represents emptiness absent of particles or fields forms a foundation of advanced cosmology. Initially, we could be inclined to picture space's vacuum as an empty void, a huge expanse lacking matter or energy. Yet, as we explore quantum mechanics' profound world, we discover a striking revelation. The vacuum isn't as empty as our classical intuition implies. Quantum mechanics, the structure that controls particles' behavior at the smallest scales, unveils a domain of exceptional activity within space's supposed emptiness. Here, the vacuum differs greatly from quiet. It teems with what scientists call quantum fluctuations. These fluctuations resemble the gentle ripples on a calm pond's surface, except they occur at the subatomic level. Within these quantum fluctuations, particles and their antiparticles participate in a brief and temporary dance of existence. They spontaneously arise from the vacuum solely to clash and annihilate one another in a short cosmic performance. These temporary events contradict our classical comprehension of emptiness and expose a dynamic and continuously changing tapestry within the vacuum. Furthermore, space's vacuum isn't simply a passive background, but an essential participant in the cosmos. It contains fields that control the universe's fundamental forces, such as the electromagnetic field. These fields spread throughout space, filling even areas we could regard as empty. In advanced cosmology's domain, it becomes clear that space's vacuum differs significantly from a genuine void. It represents a dynamic stage where the line between nothing and something becomes unclear. The vacuum exists actively with particles and fields' quantum fluctuations challenging our established notions of emptiness. Additionally, this concept carries practical consequences. Scientists utilize the energy present in these quantum fluctuations through a phenomenon called the Casimir effect. When two parallel conducting plates position close together in a vacuum, they undergo a tiny but quantifiable attraction owing to specific vacuum fluctuation suppression between them. This effect, though minor, illustrates the concrete results of the nothingness within the vacuum. What function does dark matter serve in the notion of nothing in the universe? Dark matter, this mysterious substance, which makes up a substantial portion of the universe's mass, creates an elaborate story of nothingness and the significant impact it exercises in the cosmos. Dark matter, unlike the recognizable matter that forms stars, planets, and galaxies, stays invisible to our perception. It declines to engage with light, making it undetectable through traditional observations. Yet, its gravitational existence proves undeniable, wielding a strong influence on the cosmic platform. This paradoxical characteristic makes dark matter an ideal candidate for investigating nothing's role in the universe. In the enormous cosmic web where galaxies gather like gems in the night sky, dark matter creates the concealed framework that supports the visible universe. It fills the cosmic voids and creates invisible connections that link galaxies, functioning as the cosmic adhesive binding them together. This link between galaxies would prove impossible without dark matter's presence, a substance that remains hidden within space's fabric. Dark matter's function becomes increasingly fascinating when we examine galaxies' cosmic dance. As they rotate within galaxy clusters, visible matter's gravitational attraction alone wouldn't suffice to prevent them from drifting apart. It's dark matter's invisible force with its tremendous gravitational impact that stops these galaxies from scattering into the cosmic voids. In this manner, dark matter converts space's apparent nothingness into a dynamic platform upon which galaxies execute their celestial performance. Moreover, the notion of nothing assumes new dimensions when we study the cosmos on the greatest scales. Computer simulations and observations display vast cosmic filaments like tendrils of an elaborate cosmic web where dark matter gathers. These filaments direct ordinary matter's flow, directing galaxies' formation and cosmic structures' distribution on a magnificent scale. In these seemingly vacant spaces, dark matter serves as the designer molding the universe's very structure. Dark matter's role in the concept of nothing extends beyond simple emptiness. It serves as a reminder that within the cosmic voids and space's apparent vastness, an invisible yet powerful presence exists that shapes the cosmos' fate and structure. Dark matter invites us to consider the profound relationship between nothingness and the concealed forces that shape the universe, emphasizing that even in the cosmos' most seemingly empty regions, much more exists than what we perceive. Can space ever genuinely be empty? The solution resides in cosmic background radiation's persistent whisper, a phenomenon that questions our concept of absolute nothingness. Cosmic background radiation, frequently called the cosmic microwave background, CMB, functions as an permanent remnant from our universe's earliest moments. It represents the Big Bang's afterglow itself, a cosmic reverberation that echoes through the cosmos and a proof to the primordial explosion's enduring legacy that created our universe. To grasp the link between nothing and cosmic background radiation, we must travel back in time roughly 13.8 billion years earlier. At that cosmic beginnings moment, the universe was a churning cauldron of energy and matter. Inconceivably hot and dense, photons, light's particles, were constantly released and captured in a turbulent dance, producing a blinding, cloudy fog that concealed the universe's contents. As the universe grew and cooled roughly 380,000 years following the Big Bang, a significant transformation happened. The cosmos shifted from a state of near infinite energy and density to one of relative calmness. Photons, once firmly bound with matter, obtained the liberty to travel space without constant engagement. This cosmic achievement is recognized as recombination. The photons, now liberated from matter's constraints, began a timeless voyage through the continuously expanding universe. Presently, we detect them as the cosmic microwave background radiation, a subtle glow of microwave radiation that occupies every cosmos corner. It appears as though the universe maintains within it a quiet memory of its fiery origin. This background radiation, which covers the cosmos at a frigid temperature of roughly 2.7 degrees, above absolute zero (-454.81 degrees Fahrenheit or (-270.39 degrees Celsius), represents a proof to the idea that space can never genuinely be empty. Even in the universe's most desolate and distant regions, the Big Bang's echo continues. The cosmic microwave background radiation's discovery in 1965 by Arno Penzias and Robert Wilson represented a crucial moment in our comprehension of the universe's history. It offered convincing evidence for the Big Bang theory and verified the presence of a cosmic structure that reaches far beyond the universe's visible matter. So when we contemplate whether space can ever genuinely be empty, the cosmic background radiation functions as a powerful reminder that even in the cosmos' apparent voids, traces of its vibrant history persist. How do quantum fluctuations question the idea of absolute nothingness? At the quantum scale, where particles and forces participate in a performance of probabilities, nothingness transforms into a dynamic and lively stage. Quantum mechanics, the physics branch that controls particles' behavior at the smallest scales, discloses a fundamental truth. Even lacking matter or energy, space's vacuum differs greatly from empty. Quantum fluctuations like the soft ripples on a peaceful pond's surface constitute the core of this cosmic activity. In space's seemingly empty vacuum, particles and their antimatter equivalents spontaneously appear, temporarily forming and destroying in a dance of creation and destruction. These temporary events follow Heisenberg's uncertainty principle, which permits particles to briefly defy nothingness constraints emerging from the void before disappearing back into it. These quantum fluctuations question the very idea of absolute nothingness, for they provide the vacuum with a tangible energy and liveliness. It's as if the vacuum holds a dormant vitality where particles emerge from nothing and return to nothing, leaving behind a subtle mark on space's fabric. Quantum fluctuations aren't simply theoretical concepts. They carry practical results influencing particles and fields' behavior at the quantum level. For example, they produce the phenomenon of vacuum energy, an energy form inherent in the vacuum itself. This vacuum energy is believed to contribute to the universe's accelerated expansion as detected through cosmic measurements. Moreover, quantum fluctuations create tangible impacts on particles' behavior affecting quantum field theory's predictions and subatomic particles' behavior. In laboratory experiments, these fluctuations cause phenomena like the Casimir effect, where two closely positioned parallel plates undergo a tiny but quantifiable attraction owing to certain vacuum fluctuation suppression between them. Are regions in space present where matter's density becomes extremely sparse, nearing nothing? To respond to this, we must initially acknowledge the remarkable diversity of cosmic landscapes. Our universe represents a tapestry created with matter and energy's fabric, an elaborate web of galaxies, stars, and celestial phenomena. Yet within this cosmic magnificence, we discover regions where matter's density diminishes to levels that contradict our earthly intuition. One such domain is the enormous cosmic voids, extensive, seemingly empty spaces within the cosmic tapestry. In these voids, galaxies prove uncommon and matter's density remains substantially lower than in the crowded galactic neighborhoods. These gigantic voids extend for millions of light years, and to an ordinary observer, they could seem as cosmic deserts nearing a condition of nothingness. However, the reality proves more intricate. Even in these enormous voids where galaxies are rare, a slight trace of matter still exists. Individual galaxies, cosmic dust, and dark matter's ethereal presence. Dark matter, a mysterious substance that comprises a significant portion of the universe's mass, applies its gravitational impact even in the emptiest regions, creating an invisible thread through the voids. On a greater scale, the universe itself continues expanding, and this expansion carries profound implications for nothing's concept. As galaxies drift away from each other due to the universe's expansion, regions that were once filled with matter become more thinly populated. Matter's density in these regions diminishes over cosmic time, nearing a state that might be viewed as nothingness compared to the cosmos' densely populated regions. Yet, even in the most thinly populated cosmic expanses, a subtle presence continues. Light photons traveling across the cosmos, cosmic microwave background radiation, and primordial particles' faint whispers. These traces, while exceptionally faint, endure, reminding us that even in the universe's most distant and vacant reaches, nothing represents a concept that proves difficult to define with absolute certainty. Does a link exist between the concept of nothing and the universe's expansion? The idea of nothing interweaves with one of the most significant cosmic phenomena, the universe's expansion. This link unveils a captivating tale that captures our imagination and discloses the elaborate relationship between the concept of emptiness and the cosmos' evolution. Our voyage commences with a fundamental understanding. The universe isn't static but dynamic. Galaxies like celestial islands aren't stationary in space. Rather, they remain in constant motion, consistently drifting apart from each other. This cosmic arrangement, recognized as the universe's expansion, represents a crucial piece of the puzzle that connects the concept of nothing to the enormous cosmic expanse. This connection story reveals as we look into the far past. Roughly 13.8 billion years earlier, the universe underwent an event of tremendous importance, the Big Bang. It signaled our universe's explosive birth from a singularity, a point of infinite density and temperature. At that exact moment, the universe lacked the structures and matter we witness today. It existed in a way as a state of cosmic nothingness. As the universe exploded into existence, it was inconceivably hot and dense, a churning cauldron of energy and radiation. In the early moments, particles and forces participated in a cosmic orchestra that surpasses our earthly comprehension. However, as the universe grew, it started to cool, entering a phase called recombination, roughly 380,000 years following the Big Bang. Throughout recombination, a transformative occurrence happened. At this point, the universe's temperature decreased sufficiently for electrons to merge with protons, creating the initial hydrogen atoms. This signaled the shift from a plasma of charged particles to a neutral transparent gas. The cosmos became, for the initial time, a location where light could move space without continuous scattering. This shift contains the solution to comprehending the link between nothing and the universe's expansion. It permitted light to move freely through space, transporting with it the earliest photons, the cosmic microwave background radiation. Presently, these photons fill every universe corner, functioning as a persistent remnant of the Big Bang. The cosmic microwave background radiation represents, in essence, a photograph of the universe's history, a time container from an era when the cosmos was a churning ocean of energy and matter. Its presence and the reality that we can detect it emphasizes the significant link between the concept of nothing at the universe's beginning and the cosmos' ongoing expansion. How does the concept of nothing in space connect to galaxies and stars formation? To understand this link, we must initially examine the universe's primordial state moments following the Big Bang, a catastrophic event that signaled the universe's birth roughly 13.8 billion years earlier. At that moment, the cosmos was a scorching hot, quickly expanding ocean of energy and fundamental particles, a condition of extreme density and temperature. But as the universe kept expanding and cooling, gravity arose as a controlling force, producing the formation of structures. These structures originated as minute fluctuations in matter's density within the universe's early mixture of particles. These fluctuations, though tiny, carried significant implications for the future. As the universe matured, gravity slowly drew matter together in regions where these fluctuations were marginally denser than their environment. Over ages, these regions expanded, creating the cosmic framework for galaxies. It's as if galaxy seeds were planted in space's fabric itself within the apparent nothingness. Within these primordial structures, gas and dust slowly gathered, merging into huge clouds of matter. Gravity's persistent attraction caused these clouds to compress further, resulting in stars' birth. In these infant stars' cores, nuclear fusion sparked, covering the cosmos in starlight's warm radiance. Galaxies, each holding billions or even trillions of stars, developed as cosmic cities within the enormous cosmic voids. These galaxies, extending from the graceful spirals to the mysterious ellipticals, became the centers of cosmic activity, their gravitational exchanges molding the universe's very destiny. The concept of nothing in space, far from signifying emptiness, thus appears as a surface upon which galaxies and stars' magnificent tapestry gets created. It represents the vastness between cosmic structures that permits these entities to exist. In reality, Without space's apparent nothingness, galaxies and stars wouldn't possess the cosmic platform on which to execute their celestial performance. The link between nothing and galaxies and stars formation highlights the cosmos complexity, where emptiness isn't a void, but an essential background against which the cosmic story develops. Does matter's absence in specific space parts add to black holes' creation? Black holes, frequently depicted as cosmic depths from which nothing can flee, emerge through an intricate relationship of gravity and matter's absence. These mysterious celestial objects have extensively captured astronomers' and scientists' imagination, functioning as gateways to advanced cosmology's heart. The voyage to comprehending the link between nothingness and black holes commences with massive stars. Stars, those brilliant night sky beacons, possess a limited lifespan. When a massive star arrives at its nuclear fuel's end, it experiences a catastrophic event called a supernova. The star's core collapses beneath gravity's force, producing an exceptionally dense and compact region. In this stellar death struggle, if the core mass surpasses a critical limit, it cannot resist gravity's persistent attraction. In a moment, the core implodes, compressing into an infinite decimal point of infinite density, an event called gravitational collapse. In this moment, nothingness transforms into a cosmic crucible for a black hole's birth. As the core collapses, it creates a region of such powerful gravity that not even light can flee its grip. This point of no return gets called the event horizon, and it signifies the boundary between the observable universe and the black hole's mysterious realm. Black holes appear in different sizes, from stellar mass black holes created from massive stars' remnants to supermassive black holes, which exist at galaxy centers and hold millions or even billions of times our sun's mass. Their formations process, nevertheless, stays grounded in matter's absence. In space regions where matter proves uncommon, such as the voids between galaxies, black holes' formation conditions become less common but not impossible. Stellar collisions and interactions in these empty regions can result in massive stars formation, establishing the foundation for future black hole birth. Furthermore, the enormous cosmic landscape provides ample chances for supermassive black holes' birth. These giants are believed to develop over cosmic ages as matter accumulates onto them, slowly constructing their enormous mass. Do philosophical debates exist surrounding the notion of nothing in space and its implications? The philosophical debates surrounding nothing in space echo ancient inquiries into existence's nature, the universe's origins, and reality's very essence. At these debates' center exists the fundamental question: can nothing genuinely exist? Or does it simply represent a conceptual void that our minds create to handle matter's and energy's absence? One viewpoint suggests that nothing in space isn't an empty void, but instead an intricate tapestry of quantum fluctuations, gentle ripples in spacetime's fabric, and cosmic phenomena's residue. In this perspective, even the cosmos' most seemingly empty regions teem with quantum activity, questioning the idea of a genuine void. Alternatively, another philosophical viewpoint proposes that nothingness signifies existence's absence itself, a concept beyond human understanding's grasp. It poses questions regarding nothing's very nature and whether it can be defined or measured scientifically. These philosophical debates reach to nothing's implications in space. They encourage us to examine nothingness' function in the cosmos' grand narrative. Does space's apparent emptiness function as a surface upon which the universe creates its elaborate story? Or does it represent a cosmic void that encourages us to reflect on human understanding's boundaries? Furthermore, the concept of nothing in space interweaves with ancient inquiries into extraterrestrial life's existence and distant planets' potential habitability. Philosophers and scientists contemplate whether regions of apparent cosmic nothingness might contain life beyond our planet, posing significant questions regarding life's nature itself. How has our comprehension of nothing in the cosmos developed over time through scientific discoveries and theories? The concept of nothing was frequently interwoven with philosophical and theological reflections veiled in the heavens' mystique. The skies possessed a sense of permanence and arrangement with minimal room for cosmic emptiness's notion. Nevertheless, as the scientific revolution emerged, humanity's focus moved from the abstract's domain to the empirical. Pioneering astronomers like Galileo Galilei directed their telescopes to the heavens, disclosing a cosmos filled with celestial bodies. This newfound observational accuracy destroyed the ancient views of a universe absent of activity. As the 20th century introduced a new era of scientific inquiry, the concept of nothing in the cosmos experienced a striking transformation. Relativity theory's development by Albert Einstein and quantum mechanics by Max Planck and others produced revolutionary insights. Einstein's equations disclosed spacetime's dynamic nature, while quantum mechanics revealed the quantum fluctuations that fill even space's most seemingly empty regions. One of the crucial moments in our understanding's evolution of nothing arrived with the cosmic microwave background radiation's discovery in 1965. Arno Penzias and Robert Wilson encountered this subtle afterglow of the Big Bang, a cosmic reverberation echoing through the cosmos. It supplied convincing evidence for the Big Bang theory and transformed our view of the early universe. Subsequent advances, such as the inflationary universe theory's development suggested by physicist Alan Guth in 1980, further broadened our understanding of the cosmos. This theory suggests that the universe experienced a quick and exponential expansion in its early moments, providing a persuasive explanation for the universe's observed large-scale structure. Additionally, dark matters and dark energy study, two mysterious components that constitute the majority of the universe's mass and energy, has enhanced our appreciation of nothingness in the cosmos. These invisible, mysterious entities apply their gravitational impact, molding the universe's fate and questioning our comprehension of emptiness. Presently, our understanding of nothing in the cosmos gets characterized by a significant appreciation for the elaborate dance between the visible and the invisible, the understood and the mysterious. Advanced cosmology has guided us to acknowledge that even in space's most distant regions, cosmic activity's traces continue, from quantum fluctuations to the Big Bang's echoes. What does nothing appear like or feel like? Initially, it could seem contradictory to examine nothing's appearance or sensation, for it naturally implies the absence of any detectable qualities. Yet within this contradiction exists a significant path for investigation and reflection. In the cosmos, the concept of nothing frequently evokes images of enormous dark voids where matter's and energy's absence generates an apparent emptiness. These cosmic voids extending across millions of light years could provoke a sense of isolation and quiet, an enormous expanse where the universe seems to be missing. Yet this apparent emptiness can prove misleading. Even in space's most empty regions, a subtle tapestry of activity exists. Quantum fluctuations, the soft ripples in spacetime's quantum fabric, produce temporary particle-antiparticle pairs that briefly emerge into existence and disappear, leaving behind a mark of their presence. These fluctuations, while undetectable to our senses, represent a proof to the elaborate dance between nothing and the quantum world. They remind us that even in the most seemingly empty spaces, the cosmos exists actively with activity at the smallest scales, questioning our ideas of emptiness. From a philosophical angle, the question of what nothing appears like or feels can result in introspective reflection. Some could claim that the very act of detecting or feeling nothing represents a contradiction, as perception's act assumes the presence of something to detect. In advanced cosmology's and science's domain, our capacity to understand the concept of nothing demands a careful balance between empirical observation and abstract reflection. It invites us to explore the boundaries of human cognition and to reflect on our sensory perception's limits. How does human perception and cognition shape our capacity to grasp the concept of nothing in the cosmos? Human perception, molded by our sensory organs, contributes a crucial role in our comprehension of the universe. We observe the cosmos through our eyes, ears, and other sensory apparatuses' lenses, which have developed to interpret the physical world. Nevertheless, when it involves understanding the concept of nothing in the cosmos, our senses face significant limitations. Examine the enormous cosmic voids that extend across the universe, seemingly absent of matter and energy. To our eyes, these regions seem as dark blackness, a void marked by distant starlight points. Yet this apparent emptiness conceals the elaborate quantum fluctuations and undetectable activity that happen even in space's most empty reaches. Our senses finally adjusted to the earthly world struggle to grasp the gentle quantum phenomena that support the cosmos. Quantum fluctuations, the temporary ripples in spacetime's quantum fabric, stay beyond our perception's reach. These fluctuations, while tiny, represent an essential part of the cosmic tapestry, questioning our ability to genuinely understand the concept of nothing. Cognition, the domain of thought and abstract reasoning, further complicates our quest to understand nothingness. As we reflect on nothing's nature in the universe, we discover ourselves exploring the elaborate landscape of philosophy, mathematics, and conceptual thinking. Philosophical inquiries into nothingness encourage us to investigate human thought's boundaries. Can nothing genuinely exist, or does it simply represent a conceptual construction? How do we reconcile matter's and energy's absence with quantum fluctuations and cosmic forces' persistence? Mathematics, a strong tool for modeling the cosmos, provides its own perspectives into nothingness concept. In mathematics' domain, zero signifies quantity's absence, a numerical representation of nothing. Yet, even within this mathematical abstraction, we face infinity's puzzle, an abstract concept that exceeds human intuition. How can we employ technology to transcend our own human limitations? One of the main ways technology broadens our reach is through powerful telescopes and observatories' development. These engineering wonders function as cosmic time machines, permitting us to look back in time and observe at distant galaxies, stars, and cosmic events. They capture light that has traveled the cosmos' vastness for billions of years, providing us glimpses into the universe's far past. Take, for example, the Hubble Space Telescope, a technological wonder that orbits above Earth's atmosphere. It supplies us with stunning images of galaxies, nebula, and other celestial objects, providing insights into the universe's magnificence. With its advanced instruments, Hubble has solved distant galaxies' mysteries, illuminating their formation, evolution, and supermassive black holes' presence at their centers. Similarly, ground-based observatories equipped with advanced technology permit astronomers to identify and examine cosmic phenomena that escape our unaided senses. Radio telescopes, for example, capture radio waves from celestial sources, disclosing hidden details regarding the universe, including the cosmic microwave background radiation, a Big Bang remnant. Furthermore, technology enables us to investigate the cosmos through robotic missions and space probes. These extraordinary instruments venture into space's harsh radiation-filled realms where human presence proves impossible. They collect data, capture images, and conduct experiments, broadening our comprehension of celestial bodies and their environments. One such mission is the Mars rovers, which have traveled the Martian landscape studying rocks, soil, and the planet's geology. These robotic investigators have become our eyes and hands on another planet, sending valuable data back to Earth and sparking millions' imagination. Additionally, supercomputing technology's advancement has transformed our capacity to model and simulate intricate cosmic phenomena. These strong computers process enormous data sets, permitting us to simulate galaxies, stars, and even the early universe's behavior. Through simulations, scientists obtain insights into cosmic structures, elaborate dynamics pushing our knowledge's boundaries. Now, let's examine more closely the recently launched James Webb Telescope. The James Webb Space Telescope, frequently called the JWST or Webb, represents a proof to human creativity and scientific ambition in advanced cosmology's and space exploration's field. This advanced telescope, prepared to transform the playbook of our cosmic comprehension, signifies a tremendous achievement in both engineering and scientific endeavor. Launched on December 25, 2021 aboard an Ariane 5 rocket, the JWST started its voyage to the second Lagrange point, or L2, positioned roughly 1.5 million kilometers, about 930,000 miles from Earth. This particular location was strategically selected due to its distinctive properties, supplying a stable environment largely free from Earth's atmosphere's interference and the sun's overwhelming brightness. Such conditions prove crucial for the telescope's precision observations in the infrared spectrum, a light region invisible to the human eye. The James Webb Space Telescope's primary purpose is to transform our comprehension of the cosmos by investigating the universe in extraordinary detail and depth. Unlike its predecessor, the Hubble Space Telescope, which mainly observes in visible and ultraviolet light, the JWST gets specifically designed to observe in the infrared. This capability provides it the power to disclose cosmic phenomena that have stayed hidden in darkness and mystery. The JWST gets equipped with a collection of advanced scientific instruments and detectors that permit it to look through cosmic dust clouds, disclosing stars and planetary systems' birthplaces. Its sharp infrared vision can identify distant galaxies' faint glow, permitting astronomers to investigate the universe's early periods shortly following the Big Bang. By examining the light from these distant galaxies, the telescope will provide insights into galaxies' formation and evolution over cosmic time. Additionally, the JWST is prepared to reveal planetary system secrets beyond our solar system. It will examine exoplanets and their atmospheres, supplying essential data for identifying potentially habitable worlds and progressing the search for extraterrestrial life. Its capabilities reach to characterizing exoplanets' composition and conditions, creating the way for revolutionary discoveries in the quest for habitable environments beyond Earth. Furthermore, the telescope's exact instruments permit it to explore into the universe's dark side's mysteries. It will examine dark matter's and dark energy's nature, mysterious components that constitute the cosmos majority, but stay invisible to our senses. This pursuit possesses the potential to reshape our comprehension of the fundamental forces and constituents that control the universe. In essence, the James Webb Space Telescope represents a technological wonder, a proof to human persistence and a beacon of hope for those seeking to investigate the cosmic unknown. Its mission involves not only answering existing questions, but also posing new ones, driving us further into the universe's uncharted territories. Now, let's travel beyond our current comprehension. As technology progresses and telescopes just like the JWST get launched, our search for extraterrestrial life in the cosmos persists. What if we discover life? Could we potentially be capable to discover the answers we seek from them? In recent years, excitement and anticipation surrounding exoplanets' discovery has surged. Planets orbiting stars outside our solar system. These exoplanets, numbering in the thousands, have been identified through space telescopes and observatories' careful work, such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. The remarkable number of exoplanets poses a compelling question. Could some of these distant worlds contain conditions favorable to life as we recognize it? Scientists have identified an exoplanet subset located within their star's habitable zone. Frequently called the Goldilocks zone, these planets exist at a distance from their host stars where temperatures could permit the presence of liquid water, an essential ingredient for life on Earth. To determine exoplanets' potential habitability, astronomers use an array of techniques, including exoplanet atmosphere study, surface conditions, and chemical compounds presence that might be suggestive of life processes. For example, the James Webb Space Telescope, JWST, equipped with advanced instruments, promises to transform our capacity to examine exoplanets' atmospheres and search for biosignatures such as oxygen and methane, which could suggest life's presence. Fascinatingly, exoplanets discovery has disclosed a diversity of planetary environments, from burning gas giants to rocky worlds with Earth-like characteristics. Some of these exoplanets could possess conditions that differ markedly from Earth, yet they question our assumptions about where and how life could flourish. One of the most important breakthroughs in the search for extraterrestrial life has been exoplanets detection that exist in binary star systems where two stars orbit each other. Such environments were previously regarded inhospitable to life, but recent discoveries have broadened our comprehension of potential habitable niches. Furthermore, astrobiology's field, which merges insights from astronomy, biology, and chemistry, investigates life's extremes on Earth, including extremophiles that flourish in hostile environments. These extremophiles provide insights into how life could adapt and survive on exoplanets with severe conditions. Now, let's discuss one of the many exoplanets we humans have found. The name is Proxima b. Proxima b, the mysterious exoplanet located in the star Proxima Centauri's habitable zone, invites us to investigate distant worlds' mysteries beyond our solar system. In advanced cosmology's and science's domain, Proxima b represents a proof to our unquenchable curiosity and the endless quest for knowledge regarding the cosmos. Found in 2016, Proxima b rapidly captured astronomers' and space enthusiasts' attention equally. Orbiting the closest star to our Sun, Proxima Centauri, this exoplanet exists at a distance of roughly 4.24 light-years from Earth. To place this astronomical figure into perspective, a single light-year equals about 5.88 trillion miles, making Proxima b's location a cosmic stone's throw away. Proxima b's position within the habitable zone, frequently called the Goldilocks zone, temptingly indicates that conditions on this distant world could be favorable to life as we recognize it. This orbital sweet spot suggests that Proxima b receives precisely the right amount of stellar radiation to sustain liquid water on its surface, an essential ingredient for life's emergence and maintenance. Despite its closeness to Earth, direct observations of Proxima b stay a formidable challenge. Its parent star, Proxima Centauri, is a red dwarf, considerably dimmer and cooler than our Sun. This diminutive star projects a weak illumination upon its planetary companion, complicating our efforts to examine the exoplanet's characteristics. To gather insights into Proxima b's nature, astronomers employ a variety of innovative techniques. One approach includes monitoring the star's gentle wobbles caused by the gravitational interaction with the orbiting exoplanet. By calculating these wobbles, scientists can estimate Proxima B's mass and deduce its orbital properties. Another investigation avenue utilizes the observation of starlight traveling through Proxima B's atmosphere during transits before its host star. This technique supplies a means to examine the planet's atmosphere, potentially disclosing chemical compositions, temperature gradients, and biosignatures presence. Furthermore, the James Webb Space Telescope JWST, prepared to redefine our investigation of exoplanets, provides an opportunity to examine Proxima B in extraordinary detail. Equipped with advanced infrared instruments, the JWST is anticipated to evaluate the exoplanet's atmosphere and search for clues to its habitability. We have now discussed a bit about exoplanets and how they could transform our view of extraterrestrial life in the cosmos. But let's return to this video's question. What is nothing? Is it feasible for us humans to understand what nothing genuinely is? In our search to discover an answer to this, we could initially need to learn how everything concludes, how our universe concludes. One of the most examined hypotheses concerning the universe's fate is recognized as the Big Freeze or heat death. This scenario depends on the universe's expansions concept, which was initially discovered by astronomer Edwin Hubble in the early 20th century. The Big Freeze indicates that the universe will persist to expand indefinitely, making galaxies move farther apart from one another. As the universe grows, the space between galaxies will extend, resulting in a decrease in temperature and energy density. Stars, which are the cosmic engines that drive galaxies, will ultimately exhaust their nuclear fuel and disappear into darkness. As a consequence, the universe will slowly become colder and darker with temperatures nearing absolute zero. In this frigid future, matter and energy will become more scattered, making it progressively difficult for intricate structures such as galaxies and stars to develop. Ultimately, even atoms will break down, leaving a universe dominated by particles like electrons and positrons drifting in an ocean of darkness. This state of maximum entropy and minimal energy is what scientists call the universe's heat death. Another captivating possibility is the Big Crunch. This scenario claims that the universe's expansion could ultimately reverse, causing all matter and energy to merge back into a singularity, much like the conditions that existed at the Big Bang's moment. This cyclic model indicates that the universe undergoes an infinite series of expansions and contractions. Nevertheless, current observational evidence from cosmic acceleration study and dark energy indicates that the Big Crunch scenario is less probable. Rather, it seems that the universe's expansion is accelerating, suggesting a different fate for our cosmos. Another hypothesis is the Big Rip. In this scenario, the universe's expansion accelerates to such an extreme level that it ultimately tears apart galaxies, stars, planets, and even atoms. Space's fabric itself comes apart as the expansion persists unchecked. While this concept is theoretical, it poses thought-provoking questions regarding the cosmos' ultimate fate. The investigation of the universe's ultimate fate, whether through scenarios like the Big Freeze, Big Crunch, or Big Rip, supplies valuable insights into nothing's concept in cosmology. While these scenarios depict vastly different outcomes, they all address the fundamental question of how the universe's structure, matter, and energy could evolve over cosmic time. One essential aspect of comprehending nothing in these scenarios' context is entropy's concept, a measurement of disorder and randomness in a system. The Big Freeze scenario, for example, gets associated with maximum entropy's idea, where the universe arrives at a state of ultimate disorder and minimal available energy. In this way, nothing can be viewed as organized structures' absence, such as galaxies, stars, and even particles. Alternatively, the notion of a Big Crunch or a Big Rip suggests the potential for a reverse or quick transformation of the universe, which questions our traditional notions of nothingness. It encourages us to reflect on what could exist beyond our current cosmic comprehension, particularly in extra dimensions or multiverse theories context. These cosmic scenario study also emphasizes dark energy's importance and its function in molding the universe's fate. Dark energy, a mysterious force responsible for the universe's accelerated expansion, is a concept that extends our understanding's boundaries. By exploring into dark energy's properties and its impact on cosmic evolution, scientists aim to obtain a deeper understanding of the fundamental forces at work in the cosmos. Additionally, these scenarios' exploration informs our understanding of the universe's underlying principles, spacetime's behavior, and matter's and energy's nature. This knowledge in turn adds to our capacity to define and conceptualize nothing within the cosmos context. When we think about nothing, we think of something vacant or something that doesn't exist. But what about time? Time constantly moves. Or does it? Is time a fundamental aspect of the universe, or is it a human creation to help us understand reality? One viewpoint claims that time is an intrinsic and fundamental property of the universe. This view corresponds with our everyday experiences where time seems to flow inexorably from the past to the present and forward to the future. From a clock's rhythmic ticking to the changing seasons, our lives are closely connected with time's passage. In this way, time is an unavoidable dimension of our reality, controlling events and processes unfolding. Within modern physics domain, time is a fundamental component of spacetime, a four-dimensional structure that merges space's three dimensions with time's dimension. Albert Einstein's relativity theory, which has been thoroughly tested and validated through experimentation, treats time as a dynamic and flexible entity. According to relativity, spacetime's fabric is not static but can be shaped by mass, gravity, and velocity. This viewpoint strengthens the idea that time is an intrinsic element of the universe interwoven with spacetime's geometry itself. Alternatively, a philosophical viewpoint exists that questions time's absolute nature. It proposes that our perception of time as a linear and unidirectional progression is a human mind's construction, an effective tool for organizing and understanding our experiences. From this angle, time is a mental structure we impose on the world to arrange events and establish causality. One argument supporting this viewpoint directs attention to time's relativity. Einstein's relativity theory, especially time dilation's concept, shows that time's passage can differ depending on one's relative motion or gravitational field. In other words, time is not absolute, but instead dependent on the observer's viewpoint. This insight suggests at the notion that time could be a relative concept instead of an intrinsic property of the universe. Additionally, some philosophical schools of thought argue that time is an emergent property arising from underlying physical processes' interactions. From this perspective, time is a result of physics' fundamental laws such as particles, fields, and energy's behavior. In this view, time is a human creation, a tool we employ to navigate and understand causality's intricate web in the universe. Are regions of the universe present where time conducts differently? And if so, what could this reveal about time's nature itself? One of Einstein's relativity theory's key principles is time dilation's notion. Time dilation proposes that time can elapse at different rates for observers in different motion states or experiencing different gravitational fields. This phenomenon has been experimentally validated and has practical implications for technologies like the Global Positioning System (GPS), where satellites in orbit undergo slightly different gravitational fields and consequently need to account for relativistic effects to supply accurate positioning information. In regions of powerful gravitational fields, such as massive celestial objects' vicinity like black holes, time dilation becomes especially pronounced. As an observer nears a black hole's event horizon, the point of no return, time for that observer seems to slow down significantly when compared to an observer farther away from the black hole. This effect is recognized as gravitational time dilation and is a result of spacetime's warping by massive objects, as Einstein's general relativity theory describes. Another universe region where time conducts differently is in the cosmic expansion. The universe itself is growing, and this expansion shapes time's passage. As the universe grows, galaxies and objects within it drift away from each other, causing the light they release to undergo a redshift. This redshift not only influences light's observed color, but also the frequency and time's passage itself. Observers in different galaxies could perceive time's flow differently due to the cosmic expansion. Moreover, in quantum mechanics domain, subatomic particles' behavior can question our intuitive comprehension of time. Quantum phenomena such as entanglement and superposition propose that particles can exist in multiple states at once, contradicting the classical idea of time as a linear progression of events. Could time travel be theoretically feasible? And what are the paradoxes and challenges linked with it? In theoretical physics domain, several theories exist that propose time travel could be theoretically feasible, although accomplishing it stays a tremendous technological and scientific obstacle. Some of the most remarkable concepts that drive discussions about time travel include wormholes. One widespread notion is that traversable wormholes, theoretical tunnels through spacetime, might provide shortcuts to different points in time and space. Theoretical physics permits wormholes' existence, but generating and stabilizing one would demand exotic and currently unknown matter forms with negative energy, closed time-like curves, CTCs. Some solutions to Einstein's general relativity equations allow CTC's existence, which are paths in spacetime that loop back on themselves, potentially permitting closed loops in time. Nevertheless, entering and navigating these CTCs would demand exotic matter's existence with negative energy and poses paradoxes. The butterfly effect. This notion claims that even minor changes made in the past might result in profound and unpredictable consequences in the future. A time traveler stepping on a butterfly in the distant past could inadvertently modify history's course in unforeseeable ways. The bootstrap paradox. This paradox includes an object or information sent back in time in such a manner that it becomes the very thing that was initially sent. For instance, a time traveler might give Shakespeare a copy of his own works, which Shakespeare then publishes, generating a paradox. Where did the original work originate from? Conservation of energy and causality. Time travel might potentially breach fundamental principles like energy's conservation and causality. Changes made in the past might disrupt events' causal chain, resulting in logical inconsistencies. The Novikov self-consistency principle proposed by physicist Igor Novikov. This principle proposes that physics laws would conspire to stop any actions in the past that would generate paradoxes. In other words, if time travel were feasible, the universe would guarantee that paradoxes are prevented. While these paradoxes and challenges present significant obstacles to time travel's practical realization, they also function as captivating thought experiments. Now, let's discuss the multiverse's theory. Could it help us comprehend what time and space genuinely is? At its foundation, the multiverse's theory claims that our universe, which we observe as the enormous expanse of stars, galaxies, and cosmic phenomena, is not the sole universe in existence. Rather, it proposes a multiverse's existence, an enormous and diverse collection of universes, each with its own distinctive set of physical laws, constants, and properties. One of the most notable versions of the multiverse theory is quantum mechanics' many worlds interpretation. This interpretation proposes that every quantum event with multiple potential outcomes produces a branching of the universe, generating a multitude of parallel universes, each signifying one of the potential outcomes. In this perspective, the universe constantly splits into an unfathomable number of branches, including all conceivable outcomes of quantum interactions. Another facet of the multiverse theory originates from cosmological models such as inflationary cosmology. According to these models, the early universe experienced a quick phase of expansion during which different space regions grew at different rates. In some regions, the expansion stopped, permitting galaxies and stars formation, while in others, it persisted indefinitely, generating bubble universes with different physical properties. The concept of a landscape of feasible universes within string theory also adds to the multiverse theory. String theory claims that numerous possible configurations exist for the universe's fundamental building blocks, resulting in the idea that our universe is just one of many feasible configurations within this enormous landscape. Would it ever be feasible for us humans to discover the multiverse theory's answer? While the multiverse theory offers exciting possibilities, testing it offers formidable challenges due to its inherent character. The main obstacles to testing the multiverse theory include cosmic isolation. The universes within a multiverse are frequently regarded causally disconnected from one another, signifying that events in one universe would possess no direct impact on another. This cosmic isolation makes it exceptionally challenging to detect or engage with other universes. Lack of direct evidence. To date, no direct observational or experimental evidence exists for parallel universes' existence. The multiverse theory is predominantly theoretical and grounded on complex mathematical models, making it difficult to empirically confirm. Cosmic scale. The multiverse's vastness, if it exists, is beyond our current observational capacity. The sheer scale of potentially infinite universes distributed across the cosmos offers a logistical challenge in terms of collecting data or performing experiments. Nevertheless, despite these challenges, some researchers are investigating indirect ways to test the multiverse theory's aspects. Cosmic microwave background (CMB). Examining variations in the cosmic microwave background radiation, the Big Bang's afterglow, could supply insights into other universes' existence. Anomalies or patterns in the CMB might potentially indicate collisions or interactions with other universes during cosmic inflation. String theory and particle physics. String theory, a structure that includes the multiverse concept, might provide potential predictions or constraints that can be tested through high-energy particle physics experiments. Finding evidence for string theory or certain particles consistent with its predictions could indirectly support the multiverse theory's aspects. Multiverse-specific phenomena. If the multiverse theory predicts unique phenomena or physical constants' existence in other universes, then identifying these constants or detecting such phenomena might provide indirect evidence. In essence, while the multiverse theory's direct confirmation stays a formidable scientific challenge, researchers are actively investigating avenues within current knowledges and technology's bounds. But hopefully we discover an answer to this within our lifespan. We have now discussed some different space and time theories. So let's explore the last thing: the universe is constructed of matter. What precisely is matter? At its core, matter is the material substance that constitutes all physical objects, from the smallest particles to the enormous celestial bodies that fill the cosmos. Everything we observe, touch, and engage with, including ourselves, is made of matter. Matter is defined by several key properties. Massachusetts. One of matter's defining characteristics is mass. Mass is the measurement of the matter amount in an object and is usually measured in units such as kilograms or grams. It establishes an object's weight and gravitational interaction with other objects. Volume. Matter fills space, and the space amount it fills is called its volume. Different matter forms can possess different volumes, from a solid's compact density to a gas's spread-out dispersion. Particles. Matter is composed of tiny particles, each with its own distinctive properties. These particles can consist of atoms, molecules, and subatomic particles like protons, neutrons, and electrons. These particles' arrangement and behavior establish matter's physical and chemical properties. States. Matter can exist in different states, which are usually categorized as solid, liquid, gas, and in some instances, plasma. These states are determined by particles' arrangement and movement. For instance, in a solid, particles are tightly packed and possess limited movement, while in a gas, particles are more dispersed and possess greater movement freedom.
Chemical composition.
Matter can be further classified according to its chemical composition. Elements, compounds, and mixtures signify various matter forms. Elements comprise one atom type, while compounds are made of different atom types chemically connected together. Mixtures are combinations of different substances that are not chemically connected. Physical and chemical properties. Each matter type holds distinct physical and chemical properties that determine its behavior and characteristics. These properties consist of density, melting point, boiling point, conductivity, and reactivity. Matter is not a static entity, but is subject to different physical and chemical transformations through processes such as chemical reactions, nuclear reactions, and phase changes. Matter can shift from one form to another, producing the diverse array of substances and phenomena witnessed in the universe. Matter's function in the cosmos is essential to our comprehension of the universe's structure and evolution. It creates the foundation for celestial bodies, galaxies, stars, and planets. Additionally, matter engages through gravitational, electromagnetic, and nuclear forces, molding the universe's dynamics at both the cosmic and quantum scales. Now let's explore deeper into the subatomic domain and matter's various forms and states, disclosing the elaborate tapestry of the material universe. Matter is made of subatomic particles, which are atoms' building blocks. The three main subatomic particles are protons, neutrons, and electrons. Protons, positively charged particles located in atoms' nucleus core. They are essential for defining an element's identity. Neutrons, particles with no charge located alongside protons in the nucleus. They add to an atom's mass, but not its charge. Electrons, negatively charged particles that orbit the nucleus in electron clouds or energy levels. Electrons establish an atom's chemical behavior and contribute an essential role in chemical reactions. Elements are matter's purest form, each comprising a distinctive atom type determined by protons' number in its nucleus. The element's periodic table arranges all recognized elements according to their atomic number, which is protons' number. Compounds are substances created when two or more different elements chemically merge in fixed ratios. These combinations generate entirely new substances with distinct properties. Water H2O, for example, is a compound made of 2 hydrogen atoms and 1 oxygen atom. Mixtures are combinations of different substances that are not chemically connected. Unlike compounds, mixtures don't possess fixed ratios and the individual components maintain their properties. Mixtures examples consist of air, a gaseous combination, salt water, a salt and water mixture, and even trail mix. Matter exists in different states which rely on its particles' arrangement and movement. Solid. In solids, particles are tightly packed, possess fixed positions, and vibrate in place. Solids possess definite shapes and volumes. Liquid. Liquids possess particles that are more loosely packed and can shift past each other, providing them the capacity to flow. They possess a definite volume, but assume their container's shape. Gases possess particles that are widely distributed and move freely, occupying the entire container they fill. Gases possess neither definite shape nor volume. Plasma. At exceptionally high temperatures, matter can become ionized, creating a state called plasma. Plasmas are made of positively charged ions and free electrons. Stars, lightning, and neon signs are plasma's examples. Matter's diversity in its states and forms permits the complexity and variety observed in the universe. It is the substance of galaxies, stars, planets, living organisms, and everything we witness in the cosmos. Comprehending matter's properties and behavior is essential to our understanding of the natural world and the universe's scientific investigation. In our voyage through the cosmos and matter's elaborate tapestry, we have discovered the material world's vast diversity and complexity. Yet in the middle of this richness, the concept of nothing invites us to reflect on the void, the absence, and the mysterious spaces that exist between particles, objects, and even universes. From the subatomic scale, where particles seemingly appear in and out of existence in quantum fluctuations, to the cosmic scale, where space's vacuum is not genuinely empty but occupied with dark energy and cosmic background radiation. The idea of nothing questions our perceptions and ignites philosophical inquiries. Is nothing simply something's absence, or does it hold its own existence and essence? Can we genuinely understand nothingness, or does it stay an elusive and abstract concept that surpasses human cognition?